nanohub.org.
Online simulation and more for nanotechnology.
So, yeah, this is a pretty daunting task. So we were talking about resilience, cyber resilience, and specifically hardware, software co-design for resilience. So we ended up discussing sort of two problems in this area. So one, how do you know that the system does the right thing? So what you actually want it to do? That's already a very hard problem. And then we started talking about how do you know that the system doesn't do something in addition to the right thing, right? Like do the right thing and then send all those results to some malicious actor so that they know what you did. So if we just talk about, hey, how do we know the system did the right thing? Like I said, that's a very hard problem, and I think we agreed that the current state of the practice is you put a system out there, and then it fails in some way that you didn't expect. So you patch it and you hope that that patch is done, but of course it's not, so you keep patching. And one of the problems that I think we identified is that our notion of the right thing is constantly evolving. And it's probably evolving faster than hardware at this point. So the example that we kept coming back to was Spectre and Meltdown, right? So hardware was put out there, it was correct in terms of all the specifications, but then people found a way to cause that system to fail, to leak information that it should not have been leaking. And that just wasn't, like that failure mode wasn't even considered at design time, right? So that's a very challenging problem. And I think one of the things that came up yesterday and then came up in this session again is that part of the problem is these specifications have traditionally just included logical correctness, and they didn't include things, maybe they included some notion of performance, but they didn't include things like deadlines or resilience to hardware faults, energy consumption, security, tail latency type issues, right? They just kind of said, well, let's make sure that this is a logically correct program. And then this idea that things don't do something extra, this is a major problem, especially as foundries move overseas. For governments to trust that the hardware that they're putting in safety critical systems is actually doing exactly what they want and nothing in addition. And I don't know, that's where I decided it's time to just move to the woods. But of course I had to come here to report back. So at 1:45, I'm out of here. Okay, so there were a couple things that came up as sort of current or medium term directions. Well, I'm taking artistic liberty. I don't think anybody specified them that way, but I'm going to say these were some medium term directions. So I think there's clearly a need, based on our discussion, there's clearly a need for more specifications, and not just specifications of logical correctness, but specifications of behavior in these other dimensions that are essential for resilience. And more effort should be put into formal verification. Again, not just for logical correctness, but formally verifying security properties, energy properties, resilience to transient faults and that sort of thing. The work that many people are doing to try to shrink the trusted computing base is essential, and we all thought that we should keep doing that. We discussed Elsa's example this morning. I think that was a kind of neat example. In HPC environments, they reason about mean time between failure, right? And that becomes part of how systems are designed. So we heard this morning, whether you use checkpoints or not could be determined by how likely the system is to fail when you launch your simulation, right? So to me, that was a neat use of a failure specification in part of the overall system design. Maybe we could learn more from that lesson. We also talked about how software and hardware really need to they need to talk more. I think that traditionally there's been just a line, and you do not cross that line. And my own personal take is that this is sort of stunted research, in that architects don't like the software to change. They like to just mess with hardware. And software people don't like to don't like the hardware to change. They like to just write their software. But a lot of what we kept coming back to is, well, we really need more communication between these layers. And so what these interfaces should be and what they would actually communicate is one of the open challenges. So we talked about some, I don't know, kind of crazy stuff for long-term directions. And I am afraid that maybe I biased my group too much. But so one of the ideas was, well, if we really need something that we can trust to work, right? So I threw out there are single instruction set architectures. So there's just one instruction and it can execute any programmable, or in any program, right? It's Turing complete. So we could just build that and verify it, and then maybe we're done, right? Like or at least that could be a fallback path, right? You could have sort of increasingly simple architectures that are verified to some level, and that as you lose trust in the system, you could kind of force it to use a narrower part of the architecture. We talked about, well, I guess I said this one already. So just trying to specify as much of the behavior of the system as possible ahead of time so that we have some chance of verifying it. Again, maybe I'm letting my own research leak too much into this presentation, but the idea that we should set goals in these high-level dimensions and build systems that have adaptive capability as sort of a first-class object, so users can control these things. And not all users have the same constraints, right? So some people would sacrifice a lot of performance for complete security. Other people would not make that trade-off. So building systems that can actually operate in a different range of regimes would be very, very helpful. And that's a long-term research challenge. I feel like I've already spoken too much, so let me wrap it up right there.
Okay, my job is to give an organized output for a very enriched but very diverse input. So I will do it as best as I can. So my topic is resilience of wearables and healthcare. So I think in general, when people think of wearables, they mostly think of their watches in general. But there could be sophisticated, futuristic uses of wearables. And I think one of the nice things that happened out of having these wearables as watches is that people are comfortable with having some kind of wearables on them at all times. And what that does is, that increases the comfort factor of having some kind of a sensing technology aboard on you. And so I think that part we have won. Now the part that we have to win is to make the hardware and sensor design more meaningful. And we also talked about the co-design issues, so especially in the wearable context. I think oftentimes in general, hardware gets a free pass because you have the firmware on top of the hardware and then you have the software. But I think if you have co-design, there are context-aware, or in this case, in the context of wearables, there are ways in which you can design hardware, firmware, and software so that, they have meaningful outputs. So in this case, I think if you think of wearables, there could be wearables that are more critical in the sense that you would have wearables for type 1 diabetes kind of patients where you would not want the wearables to go off, and you could have the wearables where you would want, the overall goal of being able to to be able to sense the physiological signals out of every single individual. So you don't go to the doctor when something goes amiss, but you are kind of helping someone who's maybe someone like me who is going to do some analytics on healthy people and see what are the kinds of signals, integrated signals you want from a healthy individual so as to have that ground truth right? So what is the dynamic ground truth looking like? So in those cases, you could possibly have some fault, some higher degrees of fault. So the fault tolerance level and the resilience level will possibly be different depending on what you're trying to do. We also talked about the differences between reliability and resilience. So if you think of reliability, typically when something is being built, you don't expect, say if you have a watch, you don't expect to swim and have the watch intact in general. So unless of course it's the swimming watch. So there are conditions under which it is known to be, your watch or your wearable is known to be reliable. But resilience, we talked about resilience as a way in which, maybe you could go off to Mars and, your wearable would still be able to sustain the Martian environment. So we talked about the differences between reliability and resilience. And in terms of, if you think of what the futuristic wearables would look like, you can think of these wearable human physiological data sensors. You can also think of human body networks. So there is work going on at Purdue itself. Shreyas, my friend, he does work on human body networks. So, when you think of these very invasive forms of wearables, we talked about implants also within the ambit of wearables. So if you think of implants and if you think of human body networks, then you would have to consider privacy. So I think privacy is a big thing. And Ashu talked about, typically people are concerned when you're okay with stuff when, you're sick. But as a healthy person, if you're kind of giving your data for various kinds of analysis, you would want to be, aware of, what is happening to the data. So if you consider the data pipeline itself, you have to kind of think of, again, I'm taking autistic privilege, so some of that I'm kind of putting in my thoughts and my research into as well. So if you consider the variable has some limited ability to do computation. So in order to save energy, you would have to kind of pipeline that computation. So you can consider the variable as being sort of in sensor analytics, and then you have to know when to have filters and move on to the edge, and then maybe move on to the cloud. So the things to the cloud thing. So how do you do that in a manner in which you're able to maybe exploit maximum battery life, which is possibly a concern. So when you do co-design, you also think of battery technology, right? So you can be energy efficient. So sometimes you have the trade-off, depending on what the variable is, how much performance you squeeze out of the variable and how much you maintain the battery, right? The energy versus performance. So there are various trade-offs, and, control theory and paradigms like that may help. And in terms of, again, the algorithms that are there within the wearable, as the wearable is designed to do some kind of integrated sensing. So if I, as a person, if I'm wearing multiple wearables, so it's not just the one wearable interacting with another wearable that someone else is wearing, but it's my own wearables, kind of wearables that are kind of interacting. So as a person, I may have, even as a healthy person, I might start to have multiple wearables on me. So something to consider, like the interference between wearables that are there on a single person, n equals 1. I think, so another important point is people in ecology have seen that sensors often fail, even in NASA, like space habitation. So there, when they do the design, they think of these conditions where, it's not fail-safe. Things are bound to fail. So when you're creating new kinds of, hardware, software, co-design kind of concepts, you should kind of consider, have resilience from day one be put into the design of the entire system, of the entire stack. So I think we could learn from cases such as in ecology research or space research, where the design has happened keeping in mind resilience, because these are really, Martian environments, literally speaking. I think in terms of applications that are emerging, this is my last minute, we have, you can think of chemotherapy patients where the WBC count is reduced. So typically it is done in a reactive manner. On the other hand, we want to be proactive. So one of the reasons that, wearables would be really futuristic and helpful to the humankind in general is because it would trigger a proactive system rather than a reactive system. And the other thing you can think of is, computational jewelry. So wearables don't have to be these clunky, if they're designers amongst you, you can have very sophisticated jewelry kind of wearables, where it's actually a project called the Amulet project that David Kotz is leading at Dartmouth. And he has this thing called Jitesh, that is just-in-time intervention. So you kind of along the lines of having a proactive system or a reactive system, but reacting when there is the first trigger. So you basically want to handle things, nip things at the bud. The other way in which technologies are emerging or would emerge is when you have these infections in hospitals, right? So exposure to various germs. I think the other thing that is really cool, but also brings in some research challenges in terms of privacy, is human body communication. So you have to think of security inherently in human body networks. So I think those are open challenges. And from the researchy side, when you're building, these OSICs, you should possibly have these application-specific integrated circuits. They're already there, but you should think in terms of variables. If you really want variables to succeed, then you should think of the kinds of pros and cons that you want to have in your software when you're designing so OSICs on the one hand, and maybe even domain-specific languages for variables. Because I think, having this little piece of software, hardware on you, which is possibly also very attractive, would be a nice way to shape some of the in-sensor or the sensor development challenges of the future. So I think I've kind of spoken my entire time. That's it.
All right. So we talked about community resilience, and we sort of had two questions. So first, what does a resilient community look like? So what would be needed for a community to be resilient? And we ended up breaking that out into characteristics of the community, actions that the community would need to be taking, and perspectives, so broader perspectives. And then we also talked about sort of gaps in our knowledge around community resilience. So these were the characteristics. Some of them just we talked about different sorts of capitals, particularly social capital, and that importance to community resilience. We talked about things like participatory, safe-to-fail systems, diverse, distributed. So from general characteristics to kind of more specifically related to community resilience, like the social capital and the importance of that, as well as trust between community members, decision makers. In terms of actions, we talked about things like that the community should actually have a say in deciding what resilience would look like for them and how much to invest in it. The importance of having sort of mild exposure to disturbances that you get used to them and then actually learning from those. And then we said as part of that, you would of course need to be monitoring and sort of collecting data about your system to actually learn from it. And then you need to actually build in institutional memory as well to use those lessons learned in the future and make sure that they stick around even when you have, say, changes in administrations, et cetera, in a city, for example. In the perspectives, we really only had one. We kind of ran out of time, but that was really about taking a long-term sustainability perspective, and this was emphasizing the importance of slow stressors as well as long-term, as well as sort of short-term shocks, which is what we more typically think about with resilience. So thinking about how resilience relates to both of those. And then these were some of the gaps in knowledge. So talking about this relationship between rapid onset shocks and long-term stresses. How do we move to implementation? There's a lot of resilience planning, research, but maybe less actual implementation, and what would that look like? Overcoming short-term political cycles, how do we think long-term, and some others. So I'll stop there. So, great.
Okay, so Saurabh basically asked me to summarize what we have learned in the 2 days on the socio-technical resilience side of things. And in one statement, here is what I have learned about socio-technical resilience. Designing resilience in socio-technical systems is really hard. Now, let me explain why I say so. One of the things that kept coming up in our discussions was that there are many different perspectives of the actors that are involved within the entire system. The research domain itself is highly interdisciplinary. There are social scientists and a number of different areas that are represented in the research community. So bringing all those perspectives together is one of the key challenges in this domain. Now, in terms of the measurement or quantification of resilience, we talked about the fact that there are goals at different levels. There are as many goals as there are number of people involved within the community. So trying to come up with a way to reconcile all these different objectives and clearly define the resilience for the community is a big challenge. The second issue is time scale. You can talk about resilience at a short time scale, let's say a couple of days after some disaster happens, or resilience over a period of, let's say, 10 to 100 years. So when we talk about community or a city being resilient not only to disasters, but also evolution in technology. So how do you account for those? In terms of the research methods, we've talked about a number of different research challenges. One clearly is data collection. Many times it's not easy to collect data from humans and from the systems themselves. And there were a lot of discussion about creative ways, for example, as Chris pointed out in his talk today, about how he uses Twitter data and phone data as sensors. So that's one direction. One is data collection. Then we talked about modeling and simulation. Again, there are many, many different paradigms for modeling. We talked about agent-based models, game theoretic models, discrete event simulations, and on and on and on. And depending on who you talk to, they're using different kinds of modeling paradigm. And the integration of all these modeling approaches itself is a big challenge. And then the last one, experiments themselves are very hard. As Shirley pointed out, how you can do experiments at a large scale that involves infrastructures and humans in the loop. So looking at it from the design perspective, we talked about what are the key characteristics of a resilient socio-technical system, what it should have. And some of the things that we discussed were the system should have memory. So somehow, people within this community should be able to capture learning over a period of time, and that learning should persist and inform the decisions that are made along the timeline. Then we talked about decentralization. If the information is all centralized at one location, any failure can actually result in reduced performance. Then yesterday, Ilyas briefly mentioned about this notion that the system itself should be able to imagine itself and think about all the possible states in the future and how that kind of a self-referential structure can be brought into designing socio-technical resilience. And then finally, education plays a very big role in socio-technical community resilience. So that's a quick summary of what I remember. Thank you.
Hi. I will take 1 minute to quickly summarize my own understanding of the CPS from a software person's perspective. Basically, for cyber, right, the 3 words, CPS, right? For cyber, basically we need clear policies and guidelines for designing software because software is very complex and it will be even more complex. I definitely agree that we need more formal methods to build hardware, but without any specification, right? There is no way to verify, to certify the software. And how to do that? Because people are, fundamentally greedy. We are driven by implementing features. So we need certain policy to mandate that you should have clear specification. You should have clear policies to say your software should behave like this in certain situations. So for physical part, I think we should make more realistic assumption about hardware because hardware will fail and they will fail unexpectedly. For example, Spectre and Meltdown. So that's because we have a sort of an illusion about hardware to believe that hardware will work as we expected. But software people, in the future should make better, more realistic assumption. So when we put cyber and physical into one system, there is one even a bigger factor that is human. Basically, we are designing for human, and human there could be many, and they are irrational. They could be one of the largest risk factor for low resilience. So how do we design a system to take in this large number of irrational human in mind? And that's I think that's an emerging challenge. Okay, that's my very quick summary.